PhD school on symmetries. He paper on connections and related topics. This time we also will give this lecture series about the connection. I hope you enjoy. Let's welcome the.
Thank you very much for this invitation. I've come to China for something like 20 times, and this is the second visit to Limsa, and I'm very happy to be here again. So I give 4 lectures about the operator algebra, particularly theory of subfactors zones, the tensor categories, and bi-unitary connections. So a basic idea is about quantum symmetries. So classical symmetry is described by a group. As everyone knows, group theory started in Darwin theory. So we studied symmetry of roots of polynomial equation. And today, also this kind of group has been used in many different contexts in physics and mathematics. So it's clear that a group describes some kind of symmetry in some mathematical structure. But recently, in the last 20, 30 years, we have seen a new type of symmetry, which is often called a quantum symmetry. Then, from today's viewpoint, the new algebraic structure, which is generalized group structure, is some kind of tensor category. Well, I will give more precise explanation later, though I assume many of you are already familiar with this kind of notion. So this is a new algebraic structure which describes many new types of symmetry in mathematics and physics, or in many different contexts like quantum group theory or quantum invariants in low-dimensional topology, which started with joint polynomial. And then many things in the conformal field theory and more general type of quantum field theory. Many people study tensor category, or sometimes in physics recently they often say non-invertible symmetries. So there are some different mathematical approaches to study this kind of new symmetry. But in operator algebras, so theory of operator algebra is one of the sources of this kind of new structure. And yeah, of course, I'm an operator algebraist, so I'd like to explain an approach based on operator algebras. And then particularly, we have theory of subfactors initiated by von John. This was the beginning of everything. So basically, I'd like to talk about this theory. But there are many different approaches to study this kind of mathematical theory. And then in this series of lectures, there are some, even within operator algebraic theory, we have different approaches to study this kind of new structure. And so we have machinery based on bimodules over finite algebras, and also we have a theory based on endomorphisms. This approach based on endomorphisms is more naturally suitable for some topics in conformal field theory or quantum field theory, like Doppler-Haag-Robert theory. But in these two approaches, we have to deal with infinite-dimensional operator algebra, and there are bimodules or endomorphisms. Well, that's completely natural, but also from a theoretical I mean, from a practical viewpoint, it's rather difficult to handle infinite dimensional objects directly. Then there is another method called bi-unitary connection. Sometimes we drop this adjective bi-unitary and we just say connection. And this name comes from an analogy to differential geometry. But this is a purely finite dimensional thing. So this approach has an advantage of being finite dimensional everywhere. So, for example, it's possible to make explicit computation, a numerical computation on a computer. So this is actually related to quantum computer, but this is really handled on ordinary classical computers. So this is method I'd like to particularly emphasize in this series of lectures. And these are rather old topics, and these were these studies started in the 1990s for many of us. But recently, we have some renewed interest in this third approach because of its connection to topological order. So this one is related to two-dimensional topological order and tensor networks. So I understand some of you, even many of you, are interested in this kind of aspect, and you work on research topics related to this one. So because of the new relation to this kind of topics, we have renewed interest in this rather old topic in subfactor theory, and this is what I'd like to explain in this series of lectures from the beginning. So this is the basic. So I start with this background, and I start with something totally elementary and well known. So, well, I guess many of you are already familiar with these examples, but yeah, I start with something very elementary. So, I explain a notion of tensor category in a more concrete way. So I started with some example, a very basic fundamental example. So we fix a finite group G. Then consider all its unitary representations of finite dimension. Then this is a finite group, so we have only finitely many irreducible representations after unitary equivalence. We are actually interested in this kind of finiteness in a more general setting. Then for two such finitely many irreducible unitary representations, so take such chi and sigma. Then, of course, we have a notion of a tensor product. But even if they are irreducible, the tensor product pi tensor sigma is not irreducible anymore in general. So it has a irreducible decomposition. So pi tensor sigma has, this is unitary equivalence, direct sum of say rho and rho. This is multiplicity. So non-negative integer, and this rho is from this finite set. So this is irreducible decomposition. Then this tensor product operation is associative, of course. So then in the classical group theory, of course, we have associative multiplication. So this is something which generalized the classical group multiplication. So, but there's a difference. So if we have two elements in the group, the product is another single element, but this is not a single element. We have a direct sum. So this is a new thing, but somehow it's similar to a group multiplication. Then in the case of a group multiplication, of course, we have the identity of a group. So we have something similar here. So we have the identity element for this tensor product, which is the identity representation. So I write ID. This is identity representation. That is all the group elements are mapped to number 1. So this is a one-dimensional representation. So one-dimensional. Then, of course, the pi tensor identity is unitarily equivalent to pi itself. So in this sense, this is the identity for this tensor product operation. And then, so this is completely trivial. But then, so in the case of group multiplication, we also have the inverse element for any element. So we need something like that. But then, of course, the inverse representation is not possible. So inverse. So we want to have something like an inverse element in the group. But so the inverse for pi is irreducible. So we want to have a pi bar instead of pi inverse. I use the notation pi bar because this is a standard one in group representation theory. So this should be the direct analog of the group inverse element, but of course this is not possible because this is dimension 1. If this is, say, dimension 2 for any element, this is not possible. So then what we have is this one. So here, pi tensor pi bar contains the identity in this irreducible decomposition, but we have something else. So we could have something. Then actually this this identity, this equation uniquely determines pi bar. So this equation because of irreducibility. So this is irreducible. So in this way, this is the kind of inverse representation, and this is called a dual representation. So, so in this situation, we have finitely many reducible representations, and these finitely many ones are closed on the tensor product in this sense. If we make a tensor product of two representations, we get the reducible decomposition. And also among them, we have the identity representation. And also we have pi bar for each pi, for irreducible pi. And that is kind of inverse in this sense. So then this is a completely classical setting. And then we want to make some abstract generalization of this kind of thing. That's the notion of fusion categories. Actually, this is some special class of a tensor category. So fusion category is a special example of a tensor category, and I gradually explain these terminologies. So this tensor category means that we have an objects. So this category, this word category, means that we have an object and intertwiners. And in this example, objects representation, actually finite dimensional unitary representations of a fixed group. Then, for category, I mean, we have objects and morphisms. So for two representations, pi and sigma, we have a notion of morphisms, which is given by this. So if we have two representations, this is this. T. So these are representation Hilbert spaces. So pi and sigma are unitary representations. So we have representation spaces for these two representations, h pi and h sigma. Then this is B, the bound linear operator from one Hilbert space h pi to another Hilbert space h sigma. But here they are finite dimensional Hilbert spaces, so the boundedness is not basically everything is automatically bounded. So this is just a linear map, or basically matrix from h pi to h sigma. Then this intertwines these two representations in this way. So T times pi g is equal to sigma of g times T for any g. So this is an intertwining identity. So these intertwiners make morphisms in this category. And so these are, we have objects and morphisms, and so they are just an ordinary category. But this tensor, new adjective, means that we have a tensor product operation among objects. For a general category, of course, we don't have a notion of a tensor product objects. But here we have a notion of tensor category for objects. So then here we have a tensor product operation. This is basically a notion of tensor category. But then we also have a notion of a dimension here. So a dimension of I direct sum sigma, this is of course additive. And also this is multiplicative with respect to the tensor product. And of course, a dimension is a positive real positive number, positive integer. Then later, we want to have something like a dimension in a later setting. Then in a more general setting, of a tensor category later, so we have a notion abstract dimension. Then it is not an integer anymore, but still positive. Dimension is a positive real number. So could be a non-integer. Actually, we have a lot of examples where they are not the integers. So we want to have this kind of thing. Then, but then I still don't write precise definition of a tensor category or fusion category because abstract definitions are rather complicated and it's easier to understand the examples. So then the fusion part category is basically a tensor category where it's irreducible objects finitely many, only finitely. Up to equivalence. So in the case of group representation for finite group, we have only finitely many irreducible unitary representations. And if we have this kind of finiteness in a more general setting, we use the name fusion category rather than tensor category. So the name tensor category means that we have a tensor product. And then this the name fusion is somehow represents finiteness of objects. And so this name fusion is used in the context of conformal field theory. Then we often deal with this kind of finite structure, and this is why we use this name fusion category. Then, rather than going into a more precise explanation about the tensor category or fusion category, I still continue some examples. It's a classical notion of 6J function. So this is a classical tool in theory of representation, particularly in applications to physics. So it's like this. So we choose, okay, the group is fixed. Actually, in the original setting, where they use this kind of notion for physics, they use a compact group like SU2 or SU3, but in this setting, I just use just a finite group for simplicity. Then I take reducible unitary representations. Okay, so pi, sigma, lambda, mu, rho, 6. Okay, 6 representation. And this is why we say 6J. And here I use Greek letters because that's more natural for my purpose. But in the classical context in physics, they use J1, J2, J3 up to J6. So they use the letter J, and this is why they say 6J. So we have 6 kinds of character, the letter J, but now I use Greek letters. Then I make this kind of tensor product by lambda, sigma, and then this is mu, pi, mu, mu, then sigma, and then rho. Yeah. And this arrow, each arrow represents an intertwined morphism. So then, for example, here, T1, T2, T3, T4. For example, this T4 is in home. This home space intertwiner. So it's a intertwiner from pi tensor mu to rho. Then actually, so this is from this one, but here we have some extra pi. So this is actually an intertwiner from lambda tensor sigma to mu. and we have some extra pi. So this is just an identity for pi, and here we have extra sigma. So this is T2 times identity sigma. So this is on the representation space of sigma. This is the identity operator on the representation space of sigma. Then, so T2 is an intertwiner from pi tensor lambda to nu. Then we can put extra sigma here, and we also put the extra sigma here. Then this is an intertwiner of these two sides. Then, actually, so this is a Hilbert space. That is, it has a natural inner product there, because if we have two t's here, so it's from pi tensor mu to rho, but we can always take a star. So then this is for the other direction. Here we use the unitarity of a representation and Hilbert space structure. So if we have t and say s here, then we can take a star for one of them. Then we can start from rho. And like this. And we compose these intertwiners. Okay, we can compose intertwiners. Then this is an intertwiner from rho to rho. But rho is irreducible, so the intertwiner is automatically a scalar because of irreducibility. So this product, so this is a scalar. And in this way, so this is the inner product of T and S. So in this way, we have a Hilbert space structure here. Then so for each Hilbert space, we take an orthonormal basis. Use for each Hilbert space, we choose and fix an orthonormal basis because everything is finite dimensional. So we have an orthonormal basis for each of these Hilbert spaces. Then so we choose T1, T2, up to T4, everything from basis vector for each such basis. Then so we can, so here, so we have, if we fix each orthonormal basis, we have finite remaining choices for here, finite remaining choices for T1, T2, T3, and so on. And then if we make these finite remaining choices, again, we can compose this one. So here we can always the reverse this direction. This is T4 star. And here we can take the opposite direction. That's the star of this one. Then we can compose these just like this, in this way. Then this is starts from rho, and here, 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 and here. So the composition of these four intertwiners is an intertwiner from rho to rho. So this composition is a scalar. Just like this. Here we composed two intertwiners, but here we composed four intertwiners. In this way, we get a scalar. So then so in this way, so each choice of T1, T2, T3, T4, and also pi sigma, lambda, mu, rho, gives a scalar. And basically, this assignment of a scalar is called a 6J symbol. Or in another word, so we have finite remaining choices here, finite remaining choices here. So we have a finite set of scalars. So and this finite set of scalars, complex numbers, is called 6J symbol. This is the name for attached to this system. Then here, of course, we have some freedom. We have a choice for an orthonormal basis. This gives a natural equivalent relation here. So equivalence relation arising from joining of orthonormal basis. But anyway, so this finite, we want to make some more abstract version of these numbers. So we want to make some abstract axiomatization of this set of numbers. Then basically this is a notion of a flat connection. Okay, bi-unitary. But for this part, this is an extra notion, so I first ignore this part, and I just explain what bi-unitary connection is. So this name connection is comes from an analogy to differential geometry, as I said. So this part is just some kind of number. So this adjective bi-unitary means that they are unitary in some double ways. So I want to explain this notion. Then again, I talk about this example. So this example of 6J symbols arising from a finite group is a basic example, and I want to make something more general in the setting of operator algebra. I don't want to explain this. Then, so here again, so I drop labels for representations and also intertwine, and I just draw arrows. Then here, so here we have an orthonormal basis. So this is so just compose these two arrows. So then here we have so the composition gives basis vector or some orthonormal basis. Of the intertwiner space from this upper left to the lower right here. But here, this composition also gives the basis vector for the same space. So we have the same finite dimensional Hilbert space, and we have two orthonormal bases for the same space. And then composition in this way, it means basically the inner product of this vector and this vector. So this composition is just the one I wrote here. So this composition is the inner product of two basis vectors. Then, so we have the same Hilbert space, and we have two orthonormal bases, and we take the inner product of each vector, and then of course we get a unitary matrix. So this is one inter. So I have to explain unitary in double ways, but this is one of the two unitarities. So this is an easier thing. So I for this picture, actually this square, this represents this picture, represents the number given by this composition. For intertriangles. Then this matrix is a large unitary matrix. Oh, no, this one. Indexed by these two arrows and these two arrows. Then this is given, so this entry is given by this square. Okay, so here the index that here is the left and lower two arrows, and here this is upper and right two arrows. And if we fix one pair, another pair, then by composing them, we get a number. This is a number. So, and here we have finite remaining index and indices, and also finite remaining indices. So this is a finite matrix. Matrix. And what I said here is this is a unitary matrix. So this is one unitarity, which is rather trivial. But you have another unitarity, which is not trivial. This comes from Frobenius reciprocity. So another unitarity. So now we have something like lambda tensor sigma and mu. We have this kind of intertwiner. But in this station, so this is T is in on lambda with mu. But then we can move this one this side by sigma bar. And these two spaces are isomorphic, actually. So this is, say, T hat or something. This is called Frobenius reciprocity. This is known in classical representation theory of a finite this name, short Frobenius, is something like 100 years old. So, and what we can put star, then also we can put like this one. This is anti-isomorphic. Then we can reverse this tension. Then, and here actually, so this is at this stage, this is a linear isomorphism, and both are Hilbert spaces. So in order to get an isomorphism as Hilbert spaces, we have some normalization rate, but I now ignore this. So actually, okay, I should. So here we need some normalization. Constant. Isomorphism of Hilbert spaces. And actually, this normalization comes from a dimension. now omit some these coefficients, but yeah, there are some coefficients involved. Then it's something like the following. So we have, okay, I now I didn't draw some new then here, so we can reverse this thing, and then we have pi tensor mu tensor sigma bar and rho times sigma bar and mu here. So now I reversed this orientation and also this orientation. Then here everything goes to nu. So if we compose this way here, then again this composition gives the number, and also here from this one, from this to that, we have this composition of two intertwiners and another composition of two intertwiners. And this composition again gives an orthonormal basis for this Hilbert space, and this composition gives another orthonormal basis for the same Hilbert space. So we have again unitarity. This means that we have another unitary matrix for now, V, and then so this means that so this is a reflection picture. This is a horizontal reflection. So it means in the original setting, mu to mu, yeah, this. So we have this setting. So the previously we have this one, u, this one. This is the previous setting. But now this matrix V is given by a pair of these two compositions. And then this is essentially this picture, but up to normalization. Some constant times this thing. Essentially, but here we reverse some edges, so we get a complex conjugate. But then this has to be unitary, and so this V unitary. So the original numbers, so we have finitely many numbers, and if we arrange them in this way, we get a unitary matrix. But we arrange them in a different way, then again we get a unitary matrix, but up to some constant arising from dimensions. And also here we have a complex conjugate, but this doesn't affect unitarity. So because without this we also have a unitary matrix. So in this way, these numbers, 6 symbols, give entries of large unitary matrix in two ways. This is basically the meaning of bi-unitarity. And then, okay, I stop here for a break for 5 minutes. Okay. Do you have any questions? Okay, so I continue the lecture. So basically, I want to give some abstract axiomatization of this setting, but I also need one more thing. That's the long probability eigenvalues. And also eigenvectors. So I already for the previous setting. So I draw this kind of diagram. Here I have pi, lambda, sigma, pi, g. So we just look at this part. And then we can ignore pi. So it's like this. So we draw a graph here. Okay, so here I fix sigma. Okay, we ignore pi. So and we fix sigma. And we look at choices of lambda and mu. And now we are in a situation of a fixed finite group, so we have only finite remaining choices for lambda and mu. Then we draw a graph as follows. So here we have some choices for lambda, so lambda 1 dot lambda 2, lambda 3. And then we draw dot for each of mu1, mu2, mu m. Okay, and then so these are vertices of this graph. So we have two kinds of vertices on the lambda side and on the mu side, and then we draw edges like this. And this kind of thing. So the number of edges from lambda j to mu k is given by dimension of the home space of lambda j times sigma. So for this choice of lambda j, we multiply sigma from the right, and we look at the intertwiner space to mu k, and then count the dimension of this intertwiner space. And so if we have 0, we have no edge. If we have dimension 1, we have 1 edge. If we have dimension 2, we have 2 edges. Like so, we could have multiple edges like this. So in this way, we get a bipartite graph. We get a finite bipartite graph. And here, bipartite means that the set of vertices is divided into two. Two sets. So the left for this. Here we have one set of vertices. We have another set of vertices. And then here we have something. But this could be disconnected here. So this graph may be disconnected. Then, but here, so this one, but this dimension is same as this one by Flavian's reciprocity. So instead of this picture, so here we look at this one, lambda tensor sigma, sigma mu, but also lambda. So we have some multiple edges. If we have 2 edges for this picture, we also have 2 edges for the other side. So we have the same number of edges in this dimension. So from this side also, from this side, so then the situation is symmetric now. Then also we look at single vertex lambda, and then multiplicity like this. This means that we have lambda times sigma is a direct sum of multiplicity and mu k. Agreed? Then we take a dimension. Then it means that dimension lambda times dimension sigma is equal to nk mu k. Okay. Then so we assign dimension to each vertex. Okay, so each vertex represents some irreducible representation. So we have some numbers. So we have some like 1, 4, 2, or 1, 3, 5, or something. So each vertex has some number. Then and then we have some edges like this. Then here, so this number times this is a fixed. Okay, sigma is fixed. So and here we have some choices for lambda. For each of these values, we multiply dimension this fixed number. Then we have a summation of these numbers. So this nk is just a multiplicity of the edge. So if this vertex is connected in say 2 edges, we have this value with a weight 2. And if this vertex is connected with 3 edges, we add this number 3 times. So this means that we count each weight, each number with this multiplicity. And if this is 0, of course, we don't count this one. Then, so this is so this assignment, this gives us some vector. And this gives us some vector. Then, so then we have this vector, but then if we, okay, so this summation is a matrix product. I mean, some matrix basically given by adjacency matrix of this graph, because we count multiplicity of edges. So this number is given by a multiplication of the adjacency matrix and this vector. So this means that so if we have label J, if label K, this matrix say AJK is given by the number of edges of this graph. This is an adjacency matrix. Then this, and also this is also true for sigma bar. And the dimension sigma and the dimension sigma bar is the same. So this means that the vector, okay, actually we can combine them so we get a single vector. This the vector given by entries given by the dimensions. Is an eigenvector for its adjacency. matrix with eigenvalue dimension sigma. Because of this is really the eigenvector identity. So actually, this condition almost determines these numbers. But if this graph is connected this condition, this identity, this equation is my eigenvector. Determines the vector uniquely up to positive constant. Of course, we can multiply some positive number to this station, we still get an eigenvector. And actually, here also I omitted one important thing, because we have this uniqueness because of positivity of entries. Because each entry of this vector is given by the dimension of a representation that's definitely a positive number. And this positivity and this eigenvector property, then we have uniqueness of this vector up to a positive constant. And this kind of eigenvector and eigenvalue is called Aperon-Frobenius eigenvalue and eigenvector. And so, well, we have some disconnectedness issue, but I will discuss it later. So up to this connectedness issue, if we have a graph, we have Perron-Frobenius eigenvalue, which is a positive number, and also we have a Perron-Frobenius eigenvector, which has positive entries. And so this vector is unique up to positive scalar, and this positive scalar doesn't matter so much. So I basically ignore this later. So this is how it. Then I recall the previous situation. So we have here we have actually 4 graphs. So here we have a bipartite graph already in this way, but also here we have another graph, another graph, another graph. So we have 4 bipartite graphs. And in some nice situations, these 4 graphs are the same, but from this setting, they could be entirely different. So we have 4 bipartite graphs. And so we have 4 vertex sets. And so each, for example, here, we have Perron-Frobenius a vector deriving from the dimension and from this consideration, this vector is a Perron-Frobenius eigenvector for this graph, but also for this graph. Okay, so it's simultaneously. So it's simultaneously. So 2 graphs. So each So for each of the 4 vertex set, we have a vector which is given by the dimensions, and that's each vector is a Fermat-Frobenius eigenvector for 2 graphs already. And then we want to have some abstract axiomatization, and also, and also in this setting, we choose one edge from each graph to get square picture. But if we choose one edge each from each of the graph, so we choose one edge here, another edge here, then the vertices here could be different. Then we cannot match them. And if we here we have mismatch, we have mismatch of vertices. This picture represents a value 0. 0. And if we have a match, at all the 4 corners, we can make a square. And again, we compose in that one in this way, so we get a number. This picture gives a number. And we represent this number by this square. So this square picture, just as before, represents a number arising from this setting. So from an abstract viewpoint, we have 4 bipartite graphs and eigen vectors or eigenvalues for each of them. And then if we choose one edge each from these 4 graphs, and we get some number, possibly 0 in this setting, but here, and this number is an element, an entry of some large unitary matrix. Then I'd like to give an abstract axiomatization of this setting. That's a notion of bi-unitary connection. And the setting is the following. We have 4 bipartite graphs. First, we have 4 graphs. G1, G2, G3, G4, connected in this way. And it means that the vertices of G1 here and the vertices of G2 here are identical. We have the same set. So, yeah. This is the first thing. And then, actually, so I had some connectedness issue, but then it's a bit non-trivial. But for a later thing, we assume that G1 and G3 are connected. But we do not assume connectedness for G2 and G4. So in this situation, this horizontal direction and vertical direction are not symmetric. They are mostly symmetric, but here we have one thing. Actually, Sometimes, okay, but sometimes we also assume, okay, I'm a bit weak, but so at this stage, I'm a little bit vague, but we definitely need connectedness for G1, G3. Then the Perron-Frobenius eigenvalues. Okay, recall the previous setting. So for G1, this eigenvalue arrived from dimension sigma, and we have the same dimension sigma here. But here, for this one, we have dimension pi, so just different. So the Perron-Frobenius eigenvalue for G1 and G2, they are different. But for G1, G3 is the same. And we keep this equality. So for G1 and G3 are the same. And also for G2 and G4. Okay. So for two horizontal graphs, we have the same eigenvalue. For vertical graphs, we have the same eigenvalue. But these two values could be different. Then,
So working with the same set of vertices.
yeah. So here we have one set of vertices, we have another set of vertices, and these four make one set of vertices. So we have one set of vertices that is divided into four subsets.
The numbers are equal.
No. Actually, yeah, also I dropped. So in the previous setting, we had equal number, yes, in the group setting, but I dropped this equality now. The numbers could be different.
So the adjacency matrix could be a rectangle.
Yeah, that's right. Yeah. But still we have a notion of error eigenvalue. Okay, I should say that. Yeah, the vertex set. Oh. Then for each vertex has some positive number. A has a positive number. Mu A such that it's wrong, so I have cancelled this part of the blackboard. So the situation is like this G1, G2. Then so here at the upper left, corner, this vector mu given by mu A is an eigen Frobenius eigenvector for G1, G2. And similar for the other three points. then okay, with each eigenvalue given by number 3.
Mu number or vector?
Hmm?
Here it says mu is a number. Here it says mu is a
Okay, so mu a is a number, but this okay. Actually,
okay.
yeah. So, yeah, vector given by these numbers. Then other important one unitarity. So this unitarity. So the unitary matrix, the matrix given by this. This is the unitary matrix. So the right-hand side is the convention I explained. So if we make a square, I mean, if we choose 4 edges, okay, I should. This is a general setting. So I should say. Each square gives a number. Arriving from these four graphs gives a complex number. Such that this matrix. So if we so we have finitely many numbers and we divide this, I mean, we regard these numbers as indexed by pair of these two things, then this is the unitary matrix. Okay. This is one unitarity. Then I also have another unitarity. Now I explain the normalization precisely. So, no, the other one. So each vertex has a weight given by a Perron-Frobenius eigen vector. Then, so this is a horizontal reflection. So this is a new square which is of a different type from the original one. We make a reflection. Then this is the original one. This is the original thing. And this is a new value. So this is a definition. Okay. If we make this definition, if we set in this way, so using the original value, we take a complex conjugate and we have weight arising from these Perron-Frobenius eigenvector entries. And if we define the new square value in this way, this new value is also a unitary. It gives also then the new values also give a unitary matrix having fit 5. So so this means that we make so this is a cutting of this square in this way. And this means that we cut we make a cut in this way after reflection. So before reflection, we have this cutting. So this means that we have cutting like this, and then we still have a unitary matrix as before. So, so this coefficient is a precise form of the normalization constant I expressed before. I omitted this one. So if you put this constant, positive constant before this number, and we take complex conjugate, then for this cutting, we still have a unitary matrix. So this is another unitarity. So the second unitarity. So this is the end of the action. So
could you explain a little bit that what is the index in this example?
this one?
Yes, yes.
Yeah.
Index.
So we fix this one, these vertices. Okay, then we have some choices for these two edges, and these choices give an index set for this one. And so here we also have another set of choices there. So actually, we have a unitary matrix for each fixed choice of this upper left and lower right. And here we have many choices here. Here, so if we fix one vertex here, another vertex here, then we get a unitary matrix. So we have finitely many unitary matrices. Or if we make a direct sum, of course, we can regard them as a single unitary matrix. And also here, this means that we fix this way, upper right corner and lower left corner. We fix these two vertices. Again, we have a unitary matrix after this normalization. Okay, so that's that. Yeah, that's one. Okay, that's the end of the action. So we pause this assignment. Second number. Bi-unitary action. Well, sometimes we drop this adjective bi-unitary and we just say connection, but we always need bi-unitary. So this is our axiomatic setting. And then I start to explain how to use what we get from this axiomatic setting.
Could you explain a scalar square root of mu p using and versus mu a mu b?
Oh, that's a Perron-Frobenius-Eigen vector by entity.
Yeah, but why is that scalar?
Oh, okay. I explain it later. At this stage, this is just an action, no reason.
No, it's just an action.
Yes, at this stage, yes. But later, I will explain why we have this coefficient. But one reason is that, yeah, in this setting, so if we write down probability reciprocity in a more explicit way, then we naturally, automatically get this coefficient. That's one explanation. And another explanation is that later we have a notion of commuting square. Then that condition is exactly equivalent to this normalization. So we have two completely different reasons for the same question. Okay, I did. So I now start to explain what we get from this axiomatic setting, but then I have to explain something more. So we have to explain the notion of string algebra. So this name, string, has nothing to do with string theory. So this is just a name of arising from some picture. So first we fix one. So in this setting, we have 4 bipartite graphs, but we fix just one by fix one finite. Okay. In this lecture series, I always talk about finite graph. Finite bipartite graph. Okay, connected. With Perron properties. Eigenvector and we have mu. So an easy example is this one. So here, so at the top we have 3 vertices, and at the bottom we have 2 vertices. Because everything is bipartite, we always split. So this is one group of vertices, this is another group of vertices. If we draw a graph randomly, then the Perron-Froebenius eigenvector entries are complicated, and we cannot write them in a simple way. But this is an easy example. So the Perron-Froebenius eigenvector is 1, 2, square root of 3. And then, so for example, we look at this vertex. So the original value is square root of 3. This is connected to 1 and 2 with multiplicity 1 each. So we add these numbers, 1 plus 2 is square root of 3 times square root of 3. Same here. And also, if we look at this one, this is connected to only this one. So we add this single number, which is square root of 3. That is original value 1 times square root of 3. Then here we have 2. So this is connected to 2 vertices. So square root of 3 plus square root of 3. Then 2 times square root of 3. So which is the original value 2 times square root of 3. And similar. So this is a Perron-Froebenius eigenvector. This is eigenvalue. Eigenvalue squared with the eigenvector. And as I said, so I just gave this number, but these numbers are unique up to scalar, a positive scalar. So this is an easy example. Then we fix one of the vertices. And write star for it. Then and at this stage, the choice is arbitrary. So we choose this one. Okay. Actually, this is now some correct choice for some sense, but it doesn't matter so far. Now, so I just fix this single vertex. Then we look at the path starting. We look at the path starting from star. Then first, so we start from here, and we go along this graph. Then the first choice, we start from here, then we can go only here. This is the first choice. Okay, and from this vertex, on the second step, we can go along the graph. Then we have 2 choices for the next graph here. So we here go back and go here. And we draw, we want to draw this type of situation. I mean, we want to draw all the possible choices in one picture. But then here we go here, go back, then it's complicated to see. So we draw, we make a reflection of this one. So at each step, we have a vertical reflection. Then we start here, from here, then here we go this one. But here we go back this one or this one, but now we have a reflection. So the second choice is like this. Okay. And here we have another choice. And then the next choice is this one. So we can continue in this way. Then we can count the number of passes in this way. So this is the initial thing. Then here, from this to this vertex, we have only one choice, so we have one choice here. And from this vertex, we cannot go here, so we have 0 choice here. And here, from this vertex, here we have one choice, so it's 1. And here, this is one choice. And okay, here, for this vertex, we can come from here, but not from here. So we have one possibility, 0 possibility, so we have 1. And also here, 0. But then here, for this vertex, so this means that in the original setting, we go this way and go back and here, come here. Or we go here, this way, and come back here. Okay, this means that we have 2 ways. So this here, this is 1 plus 1. Okay, so we have one choice from this way and another choice this way. So 1 plus 1 is 2. Here we have 1 plus 1 is 1. Then here we have 2 ways. So here we have only 2 choices. Here we have 2 choices here, 1 choice here, so 3, 1. So we have number in this way. So for example, this means that here 3 means that we have length 1, 2, 3, 4. So this is a length. This is a path of length 4 from this vertex to this vertex. This vertex is this one originally. So from this vertex to that vertex of length 4, we have 3 choices. So 3 different paths. Okay. So this summation rule is like a Pascal triangle. So we can continue this way. So we have we can count the number of paths from the scar each vertex. Summation rule. Like the basket. Or any bipartite graph, we can apply this way. Then we want to assign each vertex. We want to assign a matrix algebra. But okay, I don't have enough time today, so we will. To a vertex of this new graph, new picture of the dimension is given by this number. So here we will assign a 2 by 2 matrix algebra, 2 by 2, 3 by 3, 1 by 1 matrix algebra in some systematic way and with some inclusion rules. So in this way, we construct finite dimensional algebra, and then a certain limit procedure, we will get an input dimensional operator algebra. Okay, so yeah, I stop here today. Do you have any questions? No question.
In definition of connection, you didn't need a special choice of the star. In definition of connection.
Okay, I will specify that because I didn't know at first.
Yes, then why there's a special choice of the star?
For here, at this stage, this is just an arbitrary choice. Yeah, so yeah, so for this A5, actually, this is a kind of correct choice, but we could start here. That doesn't make any difference at this stage.
This theorem works for general fields.
At this stage, yes. Arbitrary field. Okay. I mean, as long as we need a square root, but yeah. And then for arbitrary field, the eigenvector is not unique, but we assume that it's given. Then it's okay.
So unitary, how about unitary?
Okay, okay, yeah, the complex, yeah, that's true, yeah, the unitarity is a problem. I don't know. There should be some way. Some matrix is an inverse of something, that kind of thing looks possible, but I'm not sure. Sorry. Yeah.
What's the relation between this connection and the connection in geometry?
Oh, so this graph is a discrete analog of a manifold. Then for manifold, we have a classical notion of connection arising from some number, arising from some kind of loop. So that's the original reason for this name. And then we have classical notion of a flat connection in differential geometry. That means that some loop doesn't change the form after parallel transform. We have a direct analog, this kind of thing in this finite graph setting. That's the origin of the name. But yeah, in this way, we don't see any geometry directly.
So do we grade this algebra by the length of the?
Oh yeah, right.
Yes, a graded.
Yeah, the graded algebra. Yeah, I'll explain the grading structure next time.
Thank the speaker.
Yeah, thank you. Tomorrow at the same time.
Yes.
Difficulty too elementary.
I'm writing an